We present ProcGen3D, which reconstructs 3D objects from RGB images by synthesizing compact procedural graph abstractions, enabling generation of high-fidelity 3D assets. ProcGen3D enables high-fidelity image-to-3D reconstruction across diverse categories of procedurally generated objects by developing a sequentialized graph-based representation. Using an autoregressive transformer, we predict a procedural graph from an input image, which is then decoded by a procedural generator into a high-fidelity 3D asset. Unlike voxel point or neural field representations, our procedural generation basis captures complex 3D content in a very compact form that can be decoded into rich, production-ready 3D assets. Using a procedural generator with predefined rules, we stochastically sample abstract graph representations that capture both the structural skeleton and geometry-related attributes of the object. These procedural graphs serve as a compact and interpretable representation of the final 3D model. We adopt a GPT-style transformer to model procedural graph generation. Each graph is sequentialized into edge-based tokens, where each token encodes the spatial positions of its two endpoint vertices, along with their corresponding attributes and the attributes of the edge itself. The transformer is trained autoregressively for next token prediction, conditioned on the input RGB image. To better align the predicted graph to the input condition, we introduce a Monte Carlo Tree Search or MCTS guided sampling into our inference process. Starting from a partially generated graph, we select the most promising leaf node for further exploration. At the beginning of the search, since no children exist, the current state is expanded directly. Each expansion uses the trained transformer as a generative prior to propose new edges. We then simulate the future performance of these new edges, which is evaluated by comparing rendered masks with the estimated mask of the input image. These resulting rewards are then propagated back through the search tree. By iteratively applying these steps, our MCTS guided search steers towards graphs that maximize consistency with the input image. Here, we compare our method with state-of-the-art 3D generative models, Trellis and Wonder3D. Our approach produces reconstructions with higher fidelity and finer geometric details on diverse categories. Furthermore, our method generalizes to real-world input images, despite being trained solely on synthetic data. While baseline models typically well capture overall structure, fine-grained geometric details are often missed. In contrast, our approach produces more physically plausible and topologically consistent reconstructions. In particular, our MCTS guidance produces graphs that align more closely with the input image, yielding more accurate and consistent 3D results. Here, we show various real-world reconstructions from our method, which consistently produces high-fidelity 3D reconstruction across a diverse set of samples. Thanks for watching.